The loneliest worlds, Earth-mass rogue planets drifting through the cosmic void. Imagine Earth torn from the sun's embrace, cast into eternal night, hurtling through interstellar space at thousands of kilometers per second. No sunrise. No seasons. Just the faint glow of distant stars growing imperceptibly brighter over millions of years as this orphaned world races through the galaxy's spiral arms. This isn't science fiction anymore. In September 2020, astronomers detected something extraordinary through gravitational microlensing, OGLE 2016, BLG 1928, a rogue planet roughly the mass of Earth, wandering alone through the darkness between stars. The discovery changed everything we thought we knew about planetary systems. For decades, we assumed planets needed stars. They formed in protoplanetary disks, accreted from dust and gas swirling around young suns, forever bound by gravity to their parent stars. But OGLE 2016, BLG 1928 revealed a different story, one where entire worlds drift through space like cosmic nomads, unbound by any stellar anchor. And here's where it gets genuinely unsettling. This single detection suggests our galaxy might contain billions of these wandering worlds, possibly outnumbering stars themselves. The method that found this planet is almost poetic in its elegance. Gravitational microlensing exploits Einstein's prediction that massive objects bend spacetime, creating gravitational lenses that magnify light from distant stars. When a rogue planet passes between us and a background star, its gravity briefly focuses that starlight, creating a characteristic brightening that lasts hours to days depending on the planet's mass and velocity. The 2020 detection revealed a lensing event lasting just 41 minutes, the shortest ever recorded for a planetary mass object. This brevity told astronomers something profound: they'd caught an Earth-mass world, possibly smaller than any rogue planet previously confirmed, speeding through space completely alone. Think about what this means for planetary formation. The leading theory suggests these rogues formed in conventional solar systems but got ejected through gravitational interactions, like cosmic billiard balls knocked off the table during chaotic early planetary migration. Computer simulations of young planetary systems show this happens more often than anyone expected. When gas giants form and begin migrating inward toward their stars, they gravitationally scatter smaller worlds. Some crash into their sun. Others get flung outward into eccentric orbits. But some achieve escape velocity, breaking free entirely to wander the galaxy forever. The numbers are staggering. Statistical analysis of microlensing surveys suggests there could be one Earth-mass rogue planet for every 4 or 5 stars in our galaxy. The Milky Way contains roughly 200 billion stars, which means potentially 40 to 50 billion Earth-sized orphans drifting through interstellar space right now. Some might pass within a light year of our solar system every few million years, invisible ghosts in the cosmic night. One could be closer to us than Proxima Centauri at this very moment, and we'd have no way of knowing unless it happened to cross our line of sight to a distant star. But here's where the story takes an unexpected turn toward hope rather than cosmic horror. Some of these worlds might not be the frozen, lifeless icebergs you'd imagine. Recent research suggests that rogue planets with sufficient mass could retain enough internal heat from radioactive decay and residual formation energy to maintain liquid water beneath thick ice shells for billions of years. Think of Europa or Enceladus, moons in our own solar system with subsurface oceans kept liquid by tidal heating and internal processes despite being far from the sun's warmth. A rogue Earth-mass planet ejected from its star system billions of years ago might still have active tectonics, a molten core generating a magnetic field, and potentially even life thriving in dark oceans sealed beneath kilometers of ice. The physics makes this scenario surprisingly plausible. Earth's core temperature exceeds 5,000 degrees Celsius, maintained primarily by the decay of radioactive isotopes like uranium-238, thorium-232, and potassium-40. This heat flow keeps our planet geologically active. A rogue Earth wouldn't have sunlight, but it would retain this internal furnace for billions of years. Add a thick hydrogen atmosphere, which many ejected planets might accumulate during formation or capture during their departure, and you have a greenhouse blanket that could trap enough heat to prevent the planet from becoming a solid frozen sphere. Models suggest such worlds could maintain subsurface oceans for the entire age of the universe. Now consider the implications for astrobiology. Life on Earth emerged relatively quickly after the planet cooled enough to have liquid water, suggesting that given the right conditions, biology might be almost inevitable. If rogue planets can maintain habitable subsurface environments, then the galaxy's biosphere could extend far beyond the narrow habitable zones around stars. Life might flourish in thousands of isolated oases scattered through interstellar space, each one a completely independent evolutionary experiment running for billions of years with no stars' interference, no day-night cycles, no seasons, just the endless constancy of geothermal energy and the chemistry of dark oceans. What would such life look like? On Earth, hydrothermal vents in the deepest oceans support entire ecosystems that never see sunlight, powered instead by chemical energy from volcanic activity. Bacteria oxidize hydrogen sulfide and methane, forming the base of food chains that include bizarre creatures like giant tube worms, blind shrimp, and pale crabs. These communities prove that photosynthesis isn't necessary for complex ecosystems. Rogue planet oceans could host similar chemosynthetic biospheres, perhaps even more diverse given billions of years of uninterrupted evolution. Some scientists speculate that such worlds might actually be better for developing complex life than Earth-like planets, because they'd lack the catastrophic extinction events caused by asteroid impacts, nearby supernovae, or stellar flares that periodically sterilize surfaces exposed to space. The technology to find these worlds in large numbers is almost here. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct the most sensitive microlensing survey ever attempted. Its 2.4-meter mirror, the same size as Hubble's, will continuously monitor millions of stars in the galactic bulge, detecting the characteristic light curves created when rogue planets pass in front of them. Mission planners estimate Roman could discover hundreds of free-floating planets, including many Earth mass or smaller, building a statistical census of these wandering worlds that will revolutionize our understanding of planetary demographics. Roman's survey will answer crucial questions. How common are Earth mass rogues compared to Jupiter mass ones? Does their frequency suggest most planetary systems go through violent early phases that eject terrestrial worlds? Are there mass distributions that hint at specific formation mechanisms? The telescope's infrared capabilities might even detect the faint heat signatures of young, recently ejected planets still glowing from their formation energy, allowing direct imaging in addition to microlensing detections. But finding them is one thing. Actually visiting a rogue planet presents challenges that make interstellar travel to Proxima Centauri look straightforward. These worlds move at typical galactic orbital velocities, around 200 kilometers per second relative to the Sun. Even if one passed within a light year of Earth, matching its velocity would require more energy than we can currently generate. Chemical rockets are hopelessly inadequate. Even proposed fusion drives would struggle. You'd need something exotic, maybe a compact fusion engine, laser-pushed light sail, or antimatter drive, technologies that remain purely theoretical. Yet the scientific payoff would be transformative. A close encounter with a rogue planet would offer the first chance to study a world that formed around another star, potentially in a completely different chemical environment. Its composition would encode information about its birth system, the metallicity of its parent star, the chemistry of its protoplanetary disk. Isotopic ratios in its rocks and atmosphere would reveal its formation distance from its original sun before ejection. If it possessed a subsurface ocean, the chemistry of that water would tell us whether life emerged independently or if biology requires the specific conditions Earth provides. There's also a darker possibility worth considering. Some rogue planets might not be natural at all. A sufficiently advanced civilization facing their star's death might choose to engineer their world for survival in interstellar space. They could build fusion reactors to replace sunlight, genetically modify their biosphere for a starless existence, and set their planet on a course toward a younger star they've identified as a suitable new home. The journey might take millions of years, but for a species with no other options, it beats extinction. From our perspective, such an engineered world would look like a natural rogue planet, at least until we got close enough to detect artificial structures or anomalous heat emissions. Roman might inadvertently discover evidence of interstellar arc worlds traversing the galaxy, though distinguishing them from natural rogues would require follow-up observations beyond the telescope's capabilities. The galactic environment these planets traverse is far from empty. Interstellar space contains about 1 atom per cubic centimeter on average, mostly hydrogen and helium, with trace amounts of heavier elements. At the velocities rogue planets travel, this creates a constant particle bombardment that slowly erodes surface features and generates faint atmospheric drag. Over billions of years, this could strip away lightweight volatiles, leaving only the most tightly bound atmospheric components. But it also means rogue planets continuously sweep up interstellar material, gradually accreting new mass, perhaps even capturing enough hydrogen to build substantial atmospheres if they started with insufficient gravity to retain one initially. Radiation presents another challenge for surface habitability. Without a star's protective heliosphere or a planet's parent star to shield it from cosmic rays, a rogue world faces the full intensity of high-energy particles permeating the galaxy. Even a strong magnetic field, which an Earth-mass planet with an active core might maintain, offers limited protection. Surface radiation levels would make life impossible for any organism adapted to Earth-like conditions. This reinforces the conclusion that if life exists on rogue planets, it must hide beneath the surface, protected by kilometers of ice and rock that absorb and scatter incoming cosmic rays before they reach liquid water zones. The frequency of near-miss encounters between rogue planets and star systems is surprisingly high on galactic timescales. Statistical models suggest that every star system, including ours, experiences several close approaches by free-floating planets during its lifetime. Close here means within a few light-years, enough for gravitational interactions but not catastrophic collisions. Most pass harmlessly by, their gravitational influence too weak and transient to significantly perturb the outer reaches of planetary systems like the Oort cloud. But occasionally, pure chance might deliver a rogue planet into the inner system, where its gravity could scatter asteroids, disturb comet clouds, or even interact with existing planets. Could Earth itself be captured this way? The physics says no with current technology to detect such an approach, but theoretically, a rogue planet passing through the inner solar system could be gravitationally captured by the Sun if its velocity and trajectory aligned perfectly. It would need to lose energy somehow, perhaps through close encounters with Jupiter or by grazing Saturn's atmosphere, slowing enough to fall into a stable orbit. The odds are astronomically small, but over billions of years and across billions of star systems, low-probability events become statistical certainties somewhere. Some planetary systems likely do capture rogue worlds, adding them to their existing planetary families. In fact, some of the oddly inclined or retrograde orbits we observe in exoplanetary systems might result from captured rogues rather than in situ formation. The OGLE 2016 BLG 1928 detection used data from the optical gravitational lensing experiment, a Polish astronomical project that's been monitoring millions of stars since 1992 specifically to find microlensing events. The discovery almost didn't happen. Microlensing requires precise timing, catching the brief moment when a foreground object perfectly aligns with a background star. Miss the alignment by days or even hours, and you detect nothing. Ogle's robotic telescopes photographed the right patch of sky at exactly the right time, captured the 41-minute brightening, and sophisticated algorithms flagged it as potentially significant among thousands of other variable star observations. Confirming the detection as a planetary mass object rather than a brown dwarf or low-mass star required careful analysis of the light curve shape. The duration depends on the lensing object's mass, distance, and velocity relative to the background star. Shorter events generally indicate lower masses, but velocity and distance create degeneracies that complicate interpretation. By fitting models to the observed brightening pattern, astronomers constrain the object's mass to somewhere between 0.5 and 3 Earth masses, with 1 Earth mass being the most likely value. The lack of any accompanying longer duration lensing signal confirmed this world travels alone, with no nearby star whose gravity would create an additional brightening component. The statistical challenge in microlensing surveys is enormous. OGLE monitors hundreds of millions of stars nightly, generating petabytes of data annually. Each star's brightness varies for dozens of mundane reasons: stellar pulsations, star spots, eclipsing binary companions, instrumental noise. Identifying the rare genuine microlensing events requires machine learning algorithms trained to recognize specific light curve shapes. False positives are common. Every potential detection needs follow-up observations from multiple telescopes to confirm the signal's reality and rule out artifacts. The fact that we found even a handful of rogue Earth mass planets suggests they must be incredibly abundant, because detecting them is so difficult that we're only scratching the surface of the actual population. Roman's advantage comes from space-based observations and modern detector technology. Ground-based telescopes like OGLE face atmospheric turbulence that limits photometric precision, weather interruptions, and the inability to observe during daylight. Roman will stare continuously at the galactic bulge from beyond Earth's atmosphere, achieving unprecedented sensitivity to short-duration microlensing events. Its survey design specifically targets rogue planet detection, monitoring enough stars with sufficient cadence to catch the brief alignments that reveal these worlds. By comparing Roman's results with OGLE and other ground-based surveys, astronomers will derive accurate statistics on rogue planet populations across different mass ranges. Beyond simple detection, Roman might characterize some of these worlds. A lucky few microlensing events could occur close enough that parallax measurements from Earth and the spacecraft's L2 orbit simultaneously observe the same event from slightly different angles. This parallax breaks the mass-distance velocity degeneracy, allowing precise determination of the lensing object's properties. We might learn not just that a rogue planet exists, but exactly where it is, how fast it's moving, and its precise mass. Such detailed characterizations would be invaluable for planning potential future missions, identifying the most accessible targets for direct observation with next-generation telescopes. The formation scenarios for rogue planets divide into two main categories: ejection from planetary systems and in situ formation as isolated objects. Ejection seems to explain most massive rogues, particularly Jupiter-sized ones, because building such large planets requires the gas-rich environment of a protoplanetary disk around a forming star. But Earth-mass rogues might form directly in molecular clouds, much like stars but without accumulating enough mass to ignite fusion. These sub-brown dwarfs, sometimes called plain moons, would technically never orbit a star, not because they were ejected but because they formed independently. Distinguishing between these populations requires statistical analysis of mass distributions and spatial distributions across the galaxy. If most Earth mass rogues result from ejection, they should be chemically similar to terrestrial planets in regular solar systems, composed primarily of iron, rock, and frozen volatiles. But if significant numbers form independently, they might have exotic compositions reflecting their molecular cloud origins, perhaps more like comets than planets, with high fractions of ices and organic molecules. Future spectroscopic observations, if we can get them, might distinguish these populations by analyzing atmospheric compositions or surface properties during close stellar encounters that briefly illuminate these dark worlds. The possibility of rogue planets harboring life raises profound questions about panspermia. If biology can survive in subsurface oceans on wandering worlds, then life might spread between star systems not on meteorites blasted from planetary surfaces, but on entire planets. A rogue world ejected from a system with established biospheres could carry that life across the galaxy. If it eventually gets captured by another star, or if organisms somehow survive on its frozen surface, it could seed biology in previously sterile systems. This form of panspermia would be far more effective than meteorite transfer, because it preserves entire ecosystems rather than just hardy microbes. The galaxy's biosphere might be more interconnected than we imagine, with rogue planets serving as ferries carrying life between distant star systems over billions of years. Detecting biosignatures on rogue planets presents a seemingly impossible challenge with current technology, but future missions might attempt it. If a rogue passes extremely close to our solar system, within a few light months, powerful telescopes might detect thermal emissions from its surface or atmosphere. Spectroscopic analysis could reveal molecular oxygen, methane, or other compounds that might indicate biological processes. More speculatively, a sufficiently advanced probe could be dispatched to intercept a rogue during a close approach, using a gravity assist from Jupiter to match velocities and conduct a flyby study. The engineering would be extraordinarily complex, but not physically impossible. The cultural impact of discovering that billions of orphaned Earths drift through our galaxy would be immense. It would fundamentally alter our perception of planetary systems as stable, orderly arrangements of worlds circling stars. Instead, we'd recognize them as dynamically chaotic environments where planets regularly get ejected, captured, and scattered. Our solar system's apparent stability over 4 billion years would be revealed as somewhat unusual, a lucky arrangement that avoided the violent gravitational interactions that flung countless other worlds into the cosmic darkness. This would make Earth seem simultaneously more precious, as a survivor in a violent cosmos, and less unique, just one of countless terrestrial worlds, many wandering alone and unnoticed. The philosophical implications cut deeper. Humanity has always defined itself relative to our sun, our seasons, our day-night cycle. Agriculture, religion, navigation, timekeeping, all our cultural foundations assume a world bound to a star. But life on a rogue planet would know none of this. If intelligent beings evolved there, their understanding of the universe would be profoundly different from ours. They would see the stars not as distant suns but as the only light sources in existence, never suspecting that most stars have their own bound worlds because they'd have no reference for orbital mechanics. Their cosmology would be built on fundamentally different observations and assumptions. Contact with such a civilization, however improbable, would be the most meaningful exchange imaginable. Two species from completely different cosmic contexts sharing their understanding of reality. Roman's microlensing survey will also provide crucial data on the galactic distribution of rogue planets. Are they concentrated in the galactic plane or scattered throughout the halo? Do older stellar populations have more rogues, suggesting accumulation over time, or do younger regions show higher frequencies from recent formation and ejection events? These patterns will constrain theories of planetary system evolution and galactic dynamics. We might discover that rogue planets cluster near spiral arms where star formation is active, or that they avoid the galactic center's intense radiation environment. Each piece of statistical data adds another constraint to our understanding of how planets form, migrate, and occasionally escape their home systems. The detection of OGLE 2016, BLG 1928 also validated and refined microlensing techniques for finding low-mass objects. Previous surveys successfully detected rogue Jupiter-mass planets, but Earth mass detections remained at the limit of ground-based capabilities. Proving that 41-minute events correspond to terrestrial mass rogues rather than some other phenomenon required careful analysis of all possible alternative explanations. Could it be a binary star system at a specific orientation? A brown dwarf with unusual properties? Systematic instrumental effects? Only by eliminating these alternatives could astronomers confidently claim the first Earth mass rogue detection, establishing a template for identifying similar events in Roman's future observations. The galactic dark matter mystery might even intersect with rogue planet populations, though probably not in the way some speculative theories once proposed. Early hypotheses suggested dark matter could consist of massive compact halo objects, including rogue planets, brown dwarfs, and black holes. Subsequent observations effectively ruled this out. There simply aren't enough machos to account for dark matter. But rogue planets do contribute to baryonic dark matter, the ordinary matter that's difficult to detect because it doesn't emit light. A galaxy full of wandering worlds represents a significant invisible mass component, not enough to explain dark matter but enough to affect galactic dynamics and mass calculations derived from gravitational observations. Future detector technologies might enable direct imaging of nearby rogues. Extremely large telescopes with adaptive optic systems could potentially detect the faint thermal glow of warm young rogues ejected recently enough to still shine in infrared wavelengths. The James Webb Space Telescope's infrared sensitivity makes it capable of imaging Jupiter-mass rogues within a few dozen light-years if they're young and hot enough. Earth-mass rogues would be far more challenging, their heat signatures weaker and detection ranges shorter, but next-generation space telescopes with larger apertures and better detectors might achieve the sensitivity needed to directly image cold terrestrial mass rogues in our cosmic neighborhood. The possibility that rogue planets could collide with Earth or other solar system bodies occasionally surfaces in popular speculation, usually in catastrophist scenarios. The actual probability is vanishingly small. Space is incomprehensibly vast, and even though billions of rogues might inhabit our galaxy, the average distance between them and their trajectories make collisions with established planetary systems extraordinarily rare. When astronomers calculate these odds, they express them in events per trillion years or across millions of galaxies. Our solar system is far more likely to be disrupted by a passing star, itself an extremely rare event, than by a rogue planet collision. Still, over the galaxy's entire history, such collisions have certainly occurred, and their effects on the struck systems would be catastrophic and fascinating. If a rogue planet did enter the inner solar system, astronomers would detect it years or decades in advance, depending on its trajectory and brightness. We continuously monitor for near-Earth objects, and a planet-mass body approaching from interstellar space would be spotted by multiple surveys once it got close enough. This would provide ample time for scientific observation and, theoretically, for contingency planning, though deflecting a planet-mass object is obviously beyond any conceivable technology. More realistically, we'd simply document its passage, using every available telescope and detector to study this visitor from another star system or the interstellar medium. The energy economy of rogue planet civilizations, if they exist, would necessarily differ radically from ours. Solar power becomes impossible. Fossil fuels would be finite resources from the planet's pre-ejection era, eventually depleted. Nuclear fission could provide energy for thousands of years, but ultimately even uranium and thorium run out. Fusion offers a longer-term solution if the planet retained hydrogen in its atmosphere or oceans, but even this is finite without the sustained fusion reaction that powers stars. The only truly sustainable energy source would be geothermal heat from radioactive decay, the same process that keeps Earth's core molten. A rogue planet civilization would need to tap this deep heat efficiently, perhaps drilling to unprecedented depths or using advanced thermodynamic systems to extract useful work from relatively modest temperature gradients. Communication between rogue planets, should multiple harbor intelligent life, presents another intriguing problem. Radio signals propagating through interstellar space would take centuries or millennia to cross typical distances between nearby rogues, assuming they're scattered throughout the galaxy at average stellar spacings. Any conversation would span generations. Civilizations might exchange elaborate data packages, entire libraries of cultural and scientific knowledge, knowing the recipients won't respond within any individual's lifetime. Or they might never attempt contact, developing in complete isolation, each one a totally independent experiment in intelligence and culture, their existence unknown to all others until they develop technologies to detect each other through some means we haven't imagined. The material resources available on rogue planets would depend critically on their formation history and composition. A world ejected from a standard solar system should have differentiated structure with an iron core, rocky mantle, and whatever surface materials accumulated during formation. Mining would be technically similar to Earth, except everything operates in permanent darkness and extreme cold on the surface. But a planet that formed independently in a molecular cloud might have a completely different structure, perhaps lacking a distinct core mantle division, with exotic ice compositions and organic chemistry more reminiscent of comets than terrestrial planets. This would offer different resources and challenges, perhaps easier access to rare elements that on Earth are sequestered in the inaccessible core. Roman's microlensing campaign will overlap with other detection methods, improving our census of free-floating objects. Direct imaging surveys are finding young brown dwarfs and super-Jupiter mass rogues that still glow with formation heat. Radio observations detect magnetic fields around some of these objects. Infrared surveys map the coldest brown dwarfs, blurring the line between failed stars and massive planets. By combining all these methods, astronomers are assembling a comprehensive picture of the mass distribution of isolated objects across the galaxy, from Jupiter-mass giants down to Earth-mass terrestrials, and potentially below into super-Earth and Mars-mass ranges if detection sensitivity continues improving. The discovery of OGLE 2016 BLG 1928 represents just the beginning of rogue planet science. Within the next decade, Roman's survey will multiply known examples by orders of magnitude, transforming rogue planets from exotic curiosities into a recognized major component of galactic structure. We'll learn whether Earth-mass rogues are common or rare, whether they cluster in certain regions or distribute uniformly, whether their properties suggest primarily ejection or in situ formation. These statistics will feed back into theories of planetary formation, improving our understanding of how solar systems evolve and how often violent dynamical interactions occur during early system history. Eventually, probably not in our lifetimes but perhaps within a century or two, humanity might send probes to investigate a nearby rogue planet directly. Such a mission would require breakthrough propulsion technology and extraordinary patience, but the scientific return would justify the investment. The first close-up images of a world from another star system, analysis of its composition and structure, detection or non-detection of subsurface oceans, and potentially the most important discovery in history if life turns out to inhabit these dark refuges. That single mission would answer questions about planetary science, astrobiology, and our place in the cosmos that we can barely formulate with current knowledge. The ultimate fate of rogue planets depends on galactic evolution. Over hundreds of billions of years, star formation will cease as galaxies exhaust their gas supplies. Existing stars will age and die, becoming white dwarfs, neutron stars, or black holes. Rogue planets will continue their journeys through an increasingly dark and empty cosmos, occasionally falling into black holes or being captured by the last remaining stars during close encounters. But most will simply drift forever, slowly cooling toward absolute zero as their radioactive elements decay away. In the far future, long after the last stars have died, these frozen worlds will be among the last remaining intact structures in a universe of expanding darkness, silent monuments to the era when galaxies glowed with stellar light and planets, both bound and free, orbited through spaces still filled with energy and possibility. For now, they remain mostly invisible, these billions of orphaned Earths speeding through the space between stars. But we've seen one. We've confirmed that worlds like ours can exist without suns, that planets need not be bound to stars to persist, that the galaxy contains far more complexity than our star-centric view ever suspected. Roman will show us hundreds more, giving form and number to what was once purely theoretical. And somewhere out there in the darkness, at this very moment, a world the size of Earth races past our solar system, perhaps only light years away, its frozen surface illuminated only by starlight, its possible oceans hidden beneath ice kilometers thick, a complete planet with its own geology, chemistry, and perhaps even biology, invisible to our eyes but very real nonetheless, continuing a journey that began billions of years ago and might continue for billions more, alone in the cosmic night. One wanderer among countless others, testament to the wild diversity of worlds that fill our galaxy and the strange paths that planetary bodies can follow through space and time. Claude is AI and can make mistakes. Please double-check responses. 18:21. The mathematics of rogue planet detection reveals just how extraordinary these discoveries are. When OGLE 2016 BLG 1928 passed between Earth and that distant background star, the alignment had to be precise within microarcseconds, a tolerance so narrow that if you were standing in New York and tried to hit a target in Los Angeles, you'd need to aim with an accuracy of less than the width of a human hair. The event lasted 41 minutes because the planet was moving at approximately 150 kilometers per second relative to our line of sight, crossing the Einstein radius, the critical zone where gravitational lensing occurs, in less than an hour. Think about what this means. Astronomers had to be watching that exact star, out of hundreds of millions, during that exact 41-minute window, or the detection would never have happened. The Einstein radius itself depends on the lensing object's mass, distance, and the distance to the background star. For an Earth mass object halfway between us and a star in the galactic bulge, roughly 20,000 light-years away, the Einstein radius measures only about 1.5 astronomical units, roughly the distance from Earth to Mars. The rogue planet had to pass through this tiny cosmic bullseye for us to detect it. Given the vastness of space and the random orientations of rogue planet trajectories, the fact that we've observed even one such event tells us these planets must be extraordinarily numerous. It's like finding a single ant in a football stadium and concluding there must be millions more you haven't seen. Statistically, microlensing surveys observe millions of stars continuously for years, accumulating billions of star-hours of observation time. Each detected microlensing event represents a lottery win against astronomical odds. The short-duration events that indicate low-mass objects are the rarest because they require even more precise alignments and occur faster, giving telescopes less time to catch them. Ogle's detection efficiency for 41-minute events is probably less than 1%, meaning for every rogue Earth mass planet they detect, 99 or more pass unnoticed. This inefficiency is why the single detection implies such a large population. Consider the journey of a typical rogue planet ejected from its birth system. The ejection velocity depends on the gravitational interaction that expelled it, usually a close encounter with a giant planet during the system's chaotic early period. Computer simulations show these interactions can fling terrestrial worlds outward at velocities ranging from just above escape velocity, around 10 km per second for a solar-type star, up to several hundred kilometers per second in extreme cases. Once free of its star's gravity, the planet retains this velocity, modified only slightly by gravitational interactions with other stars it passes during its wanderings. At a typical velocity of 200 km per second, a rogue planet covers the distance from Earth to the Sun in about 2 days. In a year, it travels roughly 6.3 light-years, crossing between neighboring star systems in the galactic disk. Over a billion years, it could traverse 6,000 light-years, crossing significant portions of the galaxy's spiral arms. But unlike migrations on Earth where travelers have destinations, rogue planets have no target. They simply move in whatever direction they were ejected, their paths gradually curving under the galaxy's overall gravitational field but never truly approaching another star unless pure chance creates an encounter. The gravitational influence of the Milky Way itself shapes these trajectories in subtle ways. The galaxy's disk contains most of its mass in stars, gas, and dark matter, creating a gravitational field that constrains objects to oscillate above and below the galactic plane. A rogue planet ejected perpendicular to the disk might rise thousands of light-years above it before the galaxy's gravity pulls it back down, creating a sinusoidal path through three-dimensional space. Planets ejected parallel to the disk stay closer to the plane, weaving between stars and molecular clouds. These orbital dynamics mean rogue planets are not uniformly distributed but cluster somewhat toward the galactic plane, though with far more freedom than stars which are more tightly bound. The chemistry of rogue planets offers another window into their origins. When a planet forms around a star, it inherits that star's metallicity, the abundance of elements heavier than hydrogen and helium. Stars formed from gas clouds enriched by previous generations of supernovae have higher metallicities and tend to produce planets with more iron, rock, and heavy elements. First-generation stars from the early universe had almost no heavy elements, and any planets they formed would be compositionally bizarre by our standards, perhaps made almost entirely of hydrogen, helium, and trace lithium. A rogue planet's composition thus encodes information about when and where it formed, what generation of star system it came from, and how chemically evolved the galaxy was at its birth. If we could analyze a rogue planet's rocks, they would contain isotopic signatures from its formation. Radioactive isotopes like aluminum-26 and iron-60, produced in supernovae and injected into protoplanetary disks, decay over millions of years. Their daughter products remain as permanent records of the environment where the planet accreted. Variations in oxygen isotopes between different solar system bodies reveal mixing and transport processes in the early solar nebula. A rogue planet from another system would have different isotopic ratios. Potentially dramatically different if it formed in a region of the galaxy with different stellar populations and supernova rates. This geochemical fingerprinting could, in principle, tell us not just that a rogue planet exists but where in the galaxy it came from. Temperature profiles on rogue planets create exotic environments unknown in our solar system. At the surface, temperatures plunge to just a few degrees above absolute zero, around 50 Kelvin or minus 220 Celsius, cold enough that nitrogen and oxygen would be solid, not gases. Carbon dioxide freezes at these temperatures. Even methane becomes solid ice. The surface would be a landscape of exotic ices illuminated only by starlight and occasional cosmic ray impacts that create brief flashes of luminescence. Moving downward through the crust, temperature gradually increases according to the geothermal gradient, determined by heat flowing from the interior. For a geologically active Earth mass planet, internal temperatures could remain similar to Earth's even billions of years after ejection. The core might still reach 5,000 Kelvin, kept hot by the decay of long-lived radioactive elements. This creates a temperature range from near absolute zero at the surface to extreme heat at the core, all within a few thousand kilometers. Somewhere in between lies a sweet spot where temperature and pressure allow liquid water to exist, assuming the planet retains sufficient volatiles. The depth of this habitable zone depends on the planet's internal heat production, thermal conductivity of its rocks, and the insulating properties of overlying ice layers. Calculating this precisely requires considering the specific heat capacity of different materials, radioactive heat production rates for uranium-238, half-life 4.5 billion years, thorium-232, half-life 14 billion years, and potassium-40, half-life 1.25 billion years, and thermal conductivity through ice, rock, and potentially liquid water layers. Models suggest that for an Earth-like composition and mass, liquid water could exist anywhere from 5 to 50 kilometers beneath the surface, depending on assumptions about atmospheric insulation and internal heat flow. This is deep enough to be completely protected from cosmic radiation and surface temperature extremes, but shallow enough that geological processes like cryovolcanism might occasionally bring subsurface material to the surface. Cryovolcanism on rogue planets would be spectacular if we could observe it. On Earth, volcanoes erupt molten rock. On icy moons like Enceladus, cryovolcanoes erupt water and ice, driven by tidal heating or internal warmth. A rogue planet might have cryovolcanoes erupting liquid water onto its frozen surface, where it would instantly freeze in the near-absolute zero environment, creating bizarre ice formations and potentially depositing minerals and organic compounds from the subsurface onto the surface where future explorers could collect them. These eruption sites would be the rogue planet equivalent of hydrothermal vents, potentially habitats for any life that evolved in the dark oceans below. The lack of a nearby star means rogue planets receive no stellar wind, the stream of charged particles flowing from stars that shapes planetary magnetospheres and can strip away atmospheres over geological time. Earth's magnetosphere protects us from the solar wind, but a rogue planet faces only the much weaker interstellar medium and cosmic rays. This might actually help them retain atmospheres better than planets orbiting stars, particularly small planets that would otherwise struggle to hold on to lightweight gases. A rogue planet with a strong magnetic field generated by a molten iron core could maintain a protective bubble around itself indefinitely, creating a stable atmospheric environment for billions of years. The possibility of intelligent life on rogue planets raises fascinating questions about technological development. On Earth, astronomy motivated mathematics, navigation, and timekeeping. Observing celestial motions led to Newton's laws and eventually general relativity. But rogue planet inhabitants would see a completely static sky. Stars would appear fixed in position across generations, showing no parallax, no proper motion visible to naked eye observation, no obvious evidence of orbital mechanics. Their development of physics might follow completely different paths, perhaps focusing earlier on chemistry, thermodynamics, or biology, since these phenomena would be more readily observable than celestial mechanics. Such a civilization would face immense challenges developing space travel. On Earth, we started with the Moon, a nearby target visible in our sky, then graduated to other planets. Rogue planet inhabitants would have no moon, no nearby worlds, just the stars impossibly far away. The nearest object in their sky might be light years distant. They might develop advanced technology, even achieve nuclear fusion or antimatter production, before ever considering space travel because they'd have nowhere nearby to go. Alternatively, they might develop extraordinary propulsion systems out of necessity, since reaching even the nearest star would require relativistic velocities, leapfrogging past the chemical rockets and early fusion drives were developing. Communication technology would develop differently as well. Radio astronomy on Earth benefits from the Sun as a reference source and from observing other stellar phenomena. Rogue planet scientists would need to be far more sensitive to detect the faint signals from distant galaxies and cosmic background radiation. They might excel at low noise detection and signal processing, developing techniques beyond our current capabilities out of necessity. Their radio telescopes might be more sophisticated than ours, built deep beneath the surface ice to shield from cosmic ray interference, using the entire planet as a detector platform. The psychological and philosophical implications of life on a rogue planet deserve consideration. Human culture and psychology are deeply shaped by cycles, day and night, seasons, lunar phases, planetary motions. We organize time around these cycles, from circadian rhythms to agricultural calendars to religious observances. Rogue planet inhabitants would know none of this. Their only natural cycle would be geological, volcanic eruptions, ocean currents, perhaps seismic rhythms. Time might be perceived entirely differently, measured by biological generations or technological milestones rather than astronomical periods. Their sense of place in the cosmos would be fundamentally alien to ours, neither heliocentric nor geocentric but existing in a universe where they are truly alone in empty space, with no parent star to define home. The economics of rogue planet colonization, should humanity ever attempt it, would be challenging. These worlds offer no solar energy, making power generation difficult. They lack easy access to other celestial bodies for mining and resources. The journey to reach one would take decades or centuries with foreseeable technology. Yet they offer certain advantages: no harmful radiation from a nearby star, stable thermal environments, potential access to liquid water and organic chemistry if subsurface oceans exist, and complete isolation from whatever catastrophes might befall solar systems. A rogue planet could serve as a truly independent backup for civilization, immune to supernovae, gamma-ray bursts, or stellar evolution that threatens planets orbiting stars. Terraforming a rogue planet presents unique problems. Traditional terraforming assumes you're modifying a world already receiving sunlight, perhaps adding atmosphere or water. Rogue planets have no sunlight to modify. You'd need to provide all energy artificially, perhaps by constructing a massive fusion reactor to serve as an artificial sun, positioned above the planet or in orbit. The energy requirements would be enormous, roughly equivalent to the sun's output if you wanted Earth-like conditions. More feasibly, you might terraform subsurface volumes, creating vast underground habitats in naturally occurring caverns or excavated chambers, heated by geothermal energy, lit by artificial lighting, a planet-sized cave system supporting an entire biosphere. The search for exomoons around rogue planets adds another layer of complexity. If a planet gets ejected from its system but retains any moons it had acquired, those moons would continue orbiting the rogue planet indefinitely. They would face the same extreme surface conditions as their parent world, but tidal heating from gravitational interactions might keep some geologically active. A large moon orbiting a rogue Earth mass planet would experience flexing similar to Io around Jupiter, potentially maintaining volcanic activity for billions of years. Such a moon could be a better habitat for life than the planet itself, with surface or near-surface liquid water maintained by tidal heating rather than radioactive decay. Detecting moons around rogue planets would be extraordinarily difficult. Microlensing can theoretically reveal their presence through subtle features in the light curve, secondary brightening peaks that indicate multiple lensing masses, but distinguishing a planet-moon system from a binary planet system or just measurement noise requires exceptionally high-quality data. Roman might detect moons around some rogue planets if the systems pass close enough and if the moons are sufficiently massive, but these detections would be rare highlights among the hundreds of rogue planets discovered. The evolution of planetary systems that produce many rogues versus few has implications for habitability elsewhere. If violent early dynamical evolution is common, many systems might lose their terrestrial worlds, leaving only hot Jupiters or widely spaced cold giants. This would reduce the number of potentially habitable worlds orbiting stars, but increase the number of potentially habitable rogues drifting through space. Conversely, if most systems evolve peacefully like ours apparently did, terrestrial worlds mostly stay bound to their stars, making rogues rarer. Which scenario dominates affects our calculations of how common life might be and where we should focus our search efforts. Current exoplanet surveys find hints that violent evolution might be common. Many discovered systems show bizarre architectures: hot Jupiters impossibly close to their stars, planets on highly eccentric orbits, misaligned systems where planets orbit perpendicular or even retrograde to the star's equator. These configurations suggest dramatic early migrations and scattering events. If these systems ejected terrestrial worlds during their rearrangement, the galaxy could contain multiple rogue terrestrial planets for every stable terrestrial world still orbiting a star, making rogues the dominant planetary environment rather than an exotic exception. The habitability of rogue planets also depends on their atmospheric retention. Earth's atmosphere mass is about 5 times 10 to 18 kilograms, held by gravity with an escape velocity of 11 kilometers per second. Lighter molecules like hydrogen and helium escape over geological time, which is why Earth's atmosphere is mostly nitrogen and oxygen rather than the hydrogen-helium mix that dominates the galaxy. A rogue planet would lose atmosphere more slowly without a stellar wind stripping it away, but cosmic ray bombardment and slow thermal escape would still gradually erode lighter gases. Over billions of years, a rogue might lose significant atmosphere unless it's sufficiently massive to hold everything gravitationally or unless it has a thick enough atmosphere that the top layers protect the lower regions from escape. Interestingly, a very thick hydrogen atmosphere could actually help maintain habitability on a rogue planet. Hydrogen is an excellent greenhouse gas at high pressures, trapping infrared radiation. Models suggest that a rogue planet with a hydrogen atmosphere several hundred times more massive than Earth's atmosphere could maintain surface temperatures above freezing despite receiving no starlight, heated purely by the greenhouse effect trapping the planet's internal geothermal heat. Such a world could have liquid water on its surface rather than buried under ice, creating a fundamentally different environment, a water world with an extremely thick hydrogen sky, pressure-cooked habitability maintained by atmospheric insulation. The organic chemistry on rogue planets could be remarkably complex. Early Earth's prebiotic chemistry was driven partly by ultraviolet radiation from the Sun, which breaks apart simple molecules and allows them to recombine into more complex forms. Rogue planets lack this UV source, but they have other energy sources: radioactive decay heat, cosmic ray impacts, lightning in any atmosphere they retain, and chemical energy from hydrothermal systems. Experiments simulating prebiotic chemistry under rogue planet conditions show that complex organic molecules, including amino acids and nucleotide precursors, can still form without sunlight. Life might even originate more easily on rogues because the environment is more stable, lacking the UV radiation that damages organic molecules and the temperature swings that stress early life. The timeline for life emerging on a rogue planet could be surprisingly favorable. On Earth, life appeared within roughly 500 million years after the planet cooled enough to have liquid water. If this timeline is representative, and if rogue planets can maintain liquid water for billions of years through internal heating, then many rogues ejected early in galactic history might have harbored life for longer than Earth has existed. Life on Earth is about 3.5 billion years old. A rogue ejected 10 billion years ago, during the early galaxy when star formation rates were higher, might have had life evolving in its subsurface oceans for 10 billion years, potentially reaching complexity levels we can barely imagine. The metabolic strategies available to life on rogue planets would necessarily differ from photosynthesis. Chemosynthesis, using chemical energy from geological processes, would dominate. On Earth, chemosynthetic ecosystems exist at hydrothermal vents where bacteria oxidize hydrogen sulfide or methane, extracting energy from these reactions to build organic molecules. Similar processes could support rogue planet biospheres, powered by chemical disequilibrium between reduced compounds from the planet's interior and oxidized compounds at the ocean floor. Alternatively, radiolytic processes where radiation breaks apart water molecules, creating hydrogen and oxygen in disequilibrium, could provide energy, similar to proposed mechanisms for life in Europa's ocean. The diversity of life on a rogue planet might actually exceed Earth's in some ways. Earth's biosphere is constrained by solar energy availability and by catastrophic extinction events like asteroid impacts that periodically reset biodiversity. Rogue planet life would know no such constraints. The energy supply from geological processes would remain constant for billions of years. No asteroid impacts would threaten subsurface oceans. No nearby supernovae would sterilize the environment. Life could evolve continuously without major disruptions, potentially achieving extraordinary complexity through sheer accumulation of evolutionary innovations over vast timescales. The oldest and most stable rogue planets might host biospheres far more diverse than Earth's, despite never seeing sunlight. The question of whether intelligence could evolve on a rogue planet is debated. Some argue that environmental challenges drive intelligence, that predator-prey dynamics and resource competition create evolutionary pressure for bigger brains and more sophisticated behavior. Rogue planet oceans, with their stable conditions and presumably limited ecological niches compared to Earth's diverse environments, might not provide sufficient pressure. Others counter that intelligence can evolve anywhere life reaches sufficient complexity, that given billions of years, any stable biosphere will eventually produce intelligent observers. The debate remains unresolved because we have only one example of intelligence emerging, on Earth, insufficient data for statistical conclusions. If intelligence does evolve on rogue planets, we might never detect it. These civilizations would emit no light pollution, no heat signature distinguishable from natural geological activity, no radio signals unless they deliberately broadcast to the stars. They might exist for millions of years, build advanced technologies, explore their subsurface world extensively, and never be noticed by external observers. Only if they achieve interstellar travel and venture out into the galaxy would we encounter them. Alternatively, they might develop technologies we haven't imagined, detection methods or communication techniques that would reveal them to sufficiently advanced observers, but that we lack the sophistication to recognize. The concept of a rogue planet's habitability zone is unusual compared to stellar habitable zones. Around stars, the habitable zone is a distance range where temperatures allow liquid water on planetary surfaces, typically between Mars and Earth's orbit for a Sun-like star. For rogue planets, the habitable zone is not spatial but structural, a depth range within the planet where temperatures and pressures permit liquid water. This zone migrates slowly over billions of years as the planet cools, starting shallow and gradually deepening as surface layers freeze more solidly and internal heat dissipates. Life would need to migrate downward with this zone, adapting to progressively higher pressures and potentially different mineral environments as it descends. The magnetic fields of rogue planets could be quite strong if they maintain active dynamos. Earth's magnetic field strength at the surface is about 50 microteslas, generated by convection in the molten outer core. A rogue planet with similar internal structure would produce similar fields, possibly stronger if its core remains hotter and more convective. These fields would create magnetospheres extending thousands of kilometers into space, deflecting cosmic rays and charged particles from the interstellar medium. Aurora would still occur when particles breach the magnetic field and strike any atmosphere, but instead of solar wind particles creating aurora on Earth, rogue planet aurora would be generated by cosmic rays and interstellar plasma, creating different spectral signatures and potentially more constant displays since the particle flux would be steadier than the variable solar wind. The seismology of rogue planets would reveal their internal structure just as seismology reveals Earth's interior. Seismic waves from impacts or internal activity would propagate through the planet, their speeds and paths depending on material properties they traverse. Any subsurface ocean would create a distinct seismic signature, a low-velocity zone where waves slow down passing through liquid water. Future missions to rogue planets might deploy seismometers on the surface or drill down to install them, then use natural seismic activity or artificial detonations to map the interior, searching for evidence of liquid layers that might harbor life. The rotation rates of rogue planets would be preserved from their formation, unaltered by tidal interactions with a star. Earth rotates once every 24 hours, gradually slowing due to tidal forces from the Moon, which also recedes slowly over time. A rogue planet with no moon and no nearby massive body would maintain whatever rotation it had when ejected, potentially spinning much faster or slower than Earth. Fast rotation would create strong Coriolis effects, affecting ocean circulation and atmospheric dynamics if the planet has sufficient atmosphere. Slow rotation would create weaker or negligible Coriolis forces, with different circulation patterns in any subsurface oceans. The naming of rogue planets raises interesting questions for the astronomical community. Currently, they're designated by the survey that found them and the observation date, like OGLE 2016, BLG 1928, practical but unmemorable. As we discover hundreds through Roman's mission, a more systematic naming scheme will be needed, perhaps based on discovery order, location in the sky, or estimated distances. Unlike stars, which have accumulated names from multiple cultural traditions over millennia, rogue planets have no cultural history. We're the first generation to know they exist. The names we give them will be their only names, a unique responsibility to choose well. The artistic and cultural representations of rogue planets will evolve as public awareness grows. Science fiction has occasionally featured rogue worlds, usually as threatening objects entering solar systems or as strange frontier settings. As the reality of billions of wandering Earths becomes common knowledge, these worlds might capture public imagination differently, perhaps as symbols of resilience, worlds surviving without stars, or as metaphors for isolation and independence. Artists might create visualizations of these dark spheres illuminated by starlight, ice-covered surfaces with occasional cryovolcanoes, or imagine subsurface oceans teeming with alien life, helping people conceptualize environments so foreign to our everyday experience. Roman's mission timeline indicates first light in 2027, with the microlensing survey beginning shortly after. The survey will continuously observe the galactic bulge for several years, accumulating hundreds of rogue planet detections. Early results should appear within the first year, confirming the detection method works as expected and providing initial statistics on rogue planet populations. By the end of the mission, astronomers will have a comprehensive census of free-floating planets across a wide mass range, from Jupiter-sized giants down to potentially Mars-sized worlds if enough short-duration events are captured. This data will transform theoretical models of planetary system evolution, providing observational constraints on how often ejection occurs and under what conditions. The follow-up observations of Roman's detections will require international coordination. When Roman spots a microlensing event indicating a rogue planet, ground-based telescopes need to observe the same event simultaneously to provide parallax measurements and confirm the detection. Networks of telescopes across different continents will coordinate observations, each catching the event from slightly different angles. This multi-telescope approach will derive precise distances and masses for at least some rogues, creating a calibration sample for the larger statistical survey. The collaboration will involve observatories worldwide, democratizing rogue planet science and ensuring that this exploration of wandering worlds is a truly international effort. The public engagement opportunities surrounding rogue planet discoveries are substantial. Unlike exoplanets orbiting distant stars, which are abstract concepts for most people, rogue planets evoke clearer imagery, worlds like Earth, wandering alone, potentially passing nearby. This narrative resonates emotionally and intellectually, making rogue planet discoveries excellent vehicles for communicating astronomy and planetary science. Educational programs could use rogue planets to teach orbital mechanics, gravitational dynamics, planetary structure, and astrobiology, all through the lens of these wandering worlds. Planetarium shows could visualize the experience of living on a rogue planet, helping audiences imagine environments radically different from our sunlit world. The economics of science missions to study rogue planets will depend on detecting one close enough to reach. If a rogue passes within a few light years, a fast probe mission becomes conceivable with advanced propulsion. If the nearest remains tens of light years away, direct study stays beyond our reach for the foreseeable future. This creates an interesting situation where we might amass enormous statistical knowledge about rogue planet populations through microlensing while remaining unable to study any individual rogue in detail. Science often faces such gaps, knowing phenomena exist statistically while lacking detailed case studies. Eventually, technology will catch up, but the gap might last decades or centuries. The impact of rogue planet research on popular culture is just beginning. Science fiction will incorporate new scientific understanding, creating more realistic portrayals of these worlds. Video games might feature rogue planets as challenging environments to explore, requiring players to manage power and resources without solar energy. Films might dramatize first contact scenarios with rogue planet civilizations or humanity's first expedition to a wandering world discovered passing nearby. These cultural products will, in turn, influence public perception and possibly inspire future scientists to study these objects, creating a feedback loop between scientific discovery and cultural imagination. The theological and philosophical questions raised by rogue planets are subtle but profound. Many religious and philosophical traditions assign special significance to Earth's relationship with the Sun, seeing solar systems as divinely ordered arrangements. Rogue planets challenge this ordering, revealing that worlds need not orbit stars to exist and possibly even to harbor life. This doesn't necessarily contradict religious views, but it expands them, suggesting that if creation includes countless wandering worlds alongside conventional solar systems, the cosmos is even more vast and varied than traditional cosmologies imagined. Theologians and philosophers will integrate these discoveries into their frameworks, just as they've integrated previous astronomical revelations like the Copernican model or the existence of billions of galaxies. The search for life will increasingly need to account for rogue planet habitats. Current efforts focus almost entirely on exoplanets in stellar habitable zones, worlds where liquid water can exist on surfaces warmed by their stars. But if rogue planets can maintain subsurface oceans for billions of years and possibly harbor life, then focusing only on stellar systems might miss the majority of biospheres. Future strategies should consider how to detect biosignatures on rogues, perhaps through spectroscopy of any thin atmospheres they retain, or through detecting waste heat from biological activity that exceeds purely geological expectations, or through some yet unimagined technique that reveals the presence of life hiding beneath ice. The comparison between rogue planets and generation ships is illuminating. Humans might someday build enormous spacecraft to travel between stars, taking thousands of years to reach their destinations, entire civilizations living and dying during the voyage. Such ships would need to be self-contained, providing all necessities without external resources, powered by onboard reactors, growing food in closed ecological systems. Rogue planets are natural generation ships, existing on similar principles, self-contained worlds moving through interstellar space, powered by internal heat, potentially supporting life in closed subsurface ecosystems. In a sense, if life exists on rogues, it's already accomplishing what we might attempt with generation ships, surviving indefinitely in space without a star, proving the concept works. The discovery of OGLE 2016, BLG 1928 will be remembered as a milestone in planetary science, equivalent to the first exoplanet detection around a main sequence star in the 1990s. It confirmed that Earth-mass rogues exist and can be detected, validating theoretical predictions and opening an entirely new field of study. Future astronomy textbooks will mark this as the moment we began seriously considering that planets are not just solar system members but can exist independently throughout the galaxy, that planetary science extends beyond studying worlds circling stars to studying worlds that have escaped into the darkness, carrying